Hi, I'm Professor Seth Chandler, and this is a video regarding tests on categorical data. I want to take a look at three of them: ChiSquare, the log-likelihood test, and the Fisher exact test. I'm doing this as part of an asynchronous course called Analytic Methods for Lawyers. So these three tests have several uses, but the one I want to focus on is using it in what are called contingency tables or confusion matrices, great name, where we have categorical data on two or more groups, and we want to see whether the grouping matters. So I want to illustrate the issue with data on whether two judges behave differently in similar asylum cases. The ChiSquare test, we're going to find out, is very popular. One of the reasons is it's easy to compute. The log-likelihood is a very elegant test in that it draws on the notion of Kullback-Leibler Divergence, which you remember from previous videos is kind of a precursor to cross-entropy. And the Fisher exact test is more accurate, but it was less frequently used because it made heavy computational demands that used to be difficult. Now it can be used a lot more easily with modern computers. So I want to show in this video how and why these tests work. Let's create some data. Basically, we're going to create data in which the first column represents the judge identity, either 1 or 2, and the second value represents the asylum application decision, where 0 is to deny the application and 1 is to grant it. All right, so there's our data. Now, you remember that for categorical data as the y value, or binary data for the y value, it's appropriate to use logistic regression. We'll let, here's our data. Here are our basis functions, where J is the judge. And we should remind the Wolfram kernel that J is a categorical variable. It's not like judge 2 is twice as something as judge 1. So let's run that. We get a fitted model, and you recall we can use parameter table to find out whether things matter. And what we see is that being a judge 1 seems to have a statistically significant negative effect on whether the asylum application will be granted.
So if we have just two possible outcomes, regression does a decent job in working with problems such as the one I just posed. But what if there are three possible outcomes? Supposing the decisions the judge can make are to deny the application, grant the application, or decide to hold a hearing. And suppose Judge 1's distribution on this point is 12.85, and Judge 2's distribution is 12.28.3. And we could complicate things further by having Judge 3. Judge 3 might go 10-12-10. We can't use 0, 1, and 2 to represent the outcomes because a hearing is not twice as much as a grant. This isn't really a regression problem, and logistic regression doesn't deal with non-binary variables, or at least not directly. So what we could do is try to convert this problem into one that logistic regression can handle. And that is, we could collapse the three outcome categories into two. We could do it in three possible ways. That is, we could say, okay, let's treat deny as a 0 and grant or hold the hearing as a 1. Or we could say, let's treat grant as a 0 and deny or hold a hearing as a 1. Or we could say, let's treat hold a hearing as a 0 and deny or grant as a 1. Now, in doing this, we're losing potentially important information, but because we're collapsing categories that are distinct, but at least, technically, logistic regression would work. So I'm going to write the code to accomplish that. Hopefully you can follow it at this point. And let's run logit model fit on our first collapsed set of data. And now we see that Judge 1's identity is not statistically significant in the change in the outcome, nor is Judge 2. Now let's collapse outcomes 0 and 2, that is deny and hearing, into a 0, and let grant be a 1. So we do it that way, and we run a logit model fit now, and now it turns out that judge 2, being judge 2, is statistically significant and has a positive effect on being a 1, which would be to grant the asylum application, I think. Or we could do it this third way. Okay? And now, let's run logit model fit, and we see that being judge 2 is statistically significant. So it's hard to know what to make of this. It depends on how you collapse the data as to what outcome you get. And that is not a great result. First, because the collapsing method is somewhat arbitrary. And secondly, because we're throwing out valuable information in the process of collapse. By the way, that process of collapse is sometimes known as one versus all regression, and that you're collapsing everything else into the all category and having that go against this one category. So logistic regression's fine, but when we start to have more than two outputs, when we get out of the realm of binary data, we run into some issues. Here's another way of doing it. Supposing we think that a judge identity and asylum disposition are independent of each other. If we could form the joint distribution of judge identity and asylum disposition under that null hypothesis, and we could calculate some sort of statistic of that distribution, then we could look at a similar statistic on our distribution, on what we actually have, and see if those two statistics are sufficiently different from one another that we say that the null hypothesis is very unlikely to be true. So that's our general approach. Let's try to implement it. Okay, let's start with our counts data, and we have, this is judge 1, his or her deny, grant, hearing rate. This is judge 2, same stuff. Judge 3, same stuff. And these are just absolute numbers, but what I want for a distribution is the fraction in each. So I basically want to divide 12 by the total of all the numbers, which you can get by putting a second argument to total and say, hey, I want to go all the way down to the second level. So we'll just take this counts data and divide each element by the total number in the whole array, which happens to be 100. So we do that, and we put it in matrix form, and we get this, basically, distribution, excuse me. All right, so to proceed further, we could do it other ways, but it's awfully convenient to use two functions that I'm not sure I have discussed much before. One is array reduce, the other is normalize. Let's do array reduce first. Okay, here's some symbolic array. It's 2 by 4. And let's just see what array reduce does using f as the first argument. Array is our second argument. That's our symbolic array up there. And 1 is one of the indices along which we want to reduce this array. So let's just see what it does. Okay, so what it's doing is it's taking this function f and it is sticking in front of the columns, basically. It's reducing out the rows, the first dimension, and so we end up with a 1 by 4, or a length 4 vector. Well, that's neat, but what use is it? Well, supposing we make array reduce's first argument total. In that case, this is a nice, easy way to get the column sums of the matrix, a plus x, b plus y, etc. Okay? So, and you can see when we're done with that, we get a length 4 vector. We could do the same thing, but we could use 2 as our third argument. And basically here, we're getting rid of the columns and just trying to have some sort of function of the rows. So let's use total again, and instead of getting the column totals, now we're going to get the row totals. So array reduce can be used to both generate row totals and column totals, which is precisely what we're going to need. The next little piece we're going to need is a function called normalize. Normalize takes two arguments. The first is data, the second is a function, and it's equal to each item of the data divided by a function of the data. So normalize of some data x with a second argument of total converts numbers into fractions that add to 1. Why? Because you're dividing each element of the data x by the total of x. Let's take an example. Here's normalize of 3, 7, 10 using total as the normalization function. And we get 3/20, 7/20, and 10/20, but 10/20 is 1/2. And just recognize we could also do this using normalize as a pure function, or as a part of a pure function. Here we're going to take our original data, and we're going to say normalize that using the total function. So, now that we've got array reduce and normalize under our belts, it's all so easy. Okay, what we need to form the independent hypothesis, the null hypothesis, that the judge is independent of the disposition, is to get what are called row marginals and column marginals. So the row marginals are just basically what we've computed. It's the fraction of the total number of cases that are assigned to each judge. So we're going to start with an array reduction, and then we're going to normalize the outcome. There are our row marginals. And so, by the way, you can see, let's just go back to the data and make sure that we're okay with this. Our original counts data, where is that? Right. So here's judge 1, 12, 8, 5, so that totals 25. So judge 1 has 25 100ths, or 0.25 of the total. Here's judge 2. Judge 2 has 43 100ths, and judge 3 has 32 100ths. So let's just hope that when we actually go through this whole rigmarole, we get that. And yes, that's 25 100ths, that's 43 100ths, and that's 32 100ths. Thank goodness. We can also compute the column marginals, which tells us the total number of dispositions of each category. This would be the fraction of applications that were denied, the fraction that were granted, and the fraction on which a hearing was held. And now what we want to do is we want to use the outer function to take the probabilities of each joint outcome. So let's say we have judge 1, 1/4, times deny, 17/50ths. And that should give us, if judge is independent from disposition, that should give us the joint probability of a judge 1 denial. Similarly, supposing we take 43 100ths and multiply it by 9/50ths. That's going to, assuming things are independent, that's going to give us the probability of a judge 2 case in which the outcome was a hearing. And so the outer function, which you can look up, lets you do these sort of combinations, and let's get our expected probability array. So here's what things would look like if the judge disposition was independent from the disposition distribution. Okay? So we have what one might call an expected probability array under the null hypothesis of an independent distribution. And if we go up here, we have the observed probability array of what we actually see. And so what we might want to do is to come up with some statistic of difference. So one way we could measure difference, I'm not saying it's the best way, I am saying it's a very traditional way, but maybe not the best way, is to take each of these corresponding values, 0.12 and 0.085, and 0.08 and 0.12, and 0.05 and 0.045, and 0.12 and 0.1462, etc., and square the differences, and then divide that squared difference by a normalizing factor, which is this expected value. So for example, here we would take 0.1462 minus 0.12, that quantity squared, and divide it by 0.1462. And we could do that for all 9 values in our array, And then we could add up all the sum of the squares. In fact, for concreteness, let's really do it. Okay, so let's write a function that says that has two arguments, observed and expected, and it's going to take the difference between the observed and the expected and square it and divide that by the expected value. Okay, so there's our function, and we'll call this function OI. All right, and now let's map thread OI over, let's get this right, the original, what is it, isn't that original probability array? What did I call that thing? I called it the observed probability array. All right, let's go back. Here we go. Observed probability array, expected probability array. That's going to give us some numbers, except we need to do this at level 2. We're not doing it row at a time, we're doing it element at a time. Sorry. Right, 2 was correct, sorry. And let's flatten that so that it's not a 3 by 3 array, but it's a 1 by 9 array. And then, what function can we use to sum the squares? If you're thinking power total, you're right. And that is our chi-square statistic for our situation. And we might just be curious what the numeric value of it is, and there it is. And I'm afraid I can't resist doing the computation live, so let's give it a shot. Let's suppose we have an observed cell value. That's one of these things or one of these things, and the only trick is we have to multiply that by the number of cases that we're dealing with. So now, having gone to all the trouble of putting things so that they add up to 1, we're going to undo that, and we're going to have all the cells add up to the number of people in our data set, the number of people who have applied for asylum. So we'll call that O, that's our observed number, and we'll call the second argument to the function E, that's the number we would expect given the independence assumption, and we'll say that we're going to compute O minus E squared, the difference squared, and we're going to divide that quantity by the expected value. Okay, so there's our little function, and I don't know, should we give this function a name? We'll call it OI. All right, so now what we're going to do is we're going to map thread OI over 100 times, because we have 100 people in the data set, times our observed probability array, and 100 times our expected probability array, and we're going to get sum of squares. See that? Now what we need to do is take the sum of the squares, and maybe you remember the way to take the sum of the squares. One of the nicest ways is our friendly power total function, so we'll flatten that list so that instead of being this nested list, it's just a flat list. And then we will take the total of it, right? Take the total of the squares. So we're not going to use power total, I'm sorry. Okay, so let's evaluate the sum of the squares of these normalized residuals. And we get some elaborate fraction. We can take its numeric value. Okay, now we got a number 12.7. Let's realize what we've done. We've taken our original joint distribution, we've formed from that another distribution that would result if the judge selection and asylum disposition were independent. So we're really just starting with this matrix here. We're deriving this matrix, and then we're taking an elaborate function of this matrix and this matrix. That's what the map thread does, and then we flatten and we total. So what we have here is, through a series of steps, we go from a matrix to a statistic. This statistic has a name. It's called a chi-square statistic, but I could call it Fred. It doesn't really matter. What does matter, what's helpful, is to realize that if this difference here, if these were normally distributed, then the sum of normally distributed variables, when you square them, is a chi-square distribution with a certain degree of freedom. And if we could figure out what that degree of freedom was, then what we could do is compute a p-value. This could be our route to a p-value. The idea is we would take the survival function of the appropriate chi-square distribution. We would evaluate that survival function at this chi-square statistic value, which again I could call Fred, and that value would be a p-value. That's the probability that we would see a number this big or greater if the judge distribution and the disposition distribution were truly independent of each other. So it turns out that to some degree of approximation, this can be thought of as normally distributed. We're taking a square, and therefore we can approximate our distribution by a chi-square distribution. What degree of freedom does that chi-square distribution have? I'm just going to tell you it has r minus 1, the rows minus 1, minus the columns minus 1. Because these numbers are not totally free. That is, these numbers have an effect on this number because the sum has to be equal to 1 of them. And so that does constrain the degrees of freedom. So we have a total here, since it's a 3 by 3 matrix, we have 2 times 2, 4 degrees of freedom. So with that background, this is some little code that basically does what we just did. It was written at an earlier time. I wrote it in a slightly different way, but that's okay. And we're going to end up producing an association that contains information about this chi-square computation. You can see it there. We've got a chi-square statistic. We have some p-value. I find this incomprehensible, so let's get the numeric value of what we just computed. And I'm really hoping that when we do that, this number is going to be that 12.7 thing, and we'll see what the p-value is. And I feel great. The chi-square statistic is 12.75, just as it was when I did it by hand. And we are now able to calculate a p-value. Why is that? Well, if we plot the survival function of the chi-square chi-square distribution with 4 degrees of freedom evaluated at 12.7542. I'm sorry, evaluated at x. Let's evaluate it at some value x. And let x go from 0 to 16, for example. That's the shape we get. And if we consider what is the value at 12.75, we will get this p-value of 0.012, blah, blah, blah. Okay? So we've now calculated a p-value that determines how likely it is we would get a matrix that looks like this if, in fact, the judge was independent of the disposition. Let's automate that process. I'm going to write a function chi-square test. here's how it's going to work. We're going to take the counts matrix, and we're going to produce from that the row marginals, the column marginals, an expected probability array, and we're then going to say, here, take the observed probability array, take the expected probability array, take the number of people in the counts, and then feed it into this 3-parameter version of chi-square test. We're going to flatten the expected probability array, we're going to flatten the observed probability array, we're going to calculate the degrees of freedom, we're going to calculate a chi-square statistic, and then we're going to calculate the survival function using a chi-square distribution with the computed number of degrees of freedom and the chi-square statistic. So that's a polymorphic function. We're having two functions named chi-square test, one of which calls the other. It's a more sophisticated programming technique than perhaps I've shown you thus far, but that's what it is. So let's do that. Let's take the chi-square test with our counts data and take the numeric value. And I guess I cheated and did this earlier, but there's our result, our chi-square statistic, and our p-value. You might think, hooray, we are done. Unfortunately, we are not done. And the reason we are not done is that the chi-square test is flawed. The problem is that this statistic that we computed, that chi-square statistic, is not distributed according to a chi-square distribution. And you can kind of see that immediately in the sense that if the chi-square distribution represents, it's based on normally distributed error, you know that the difference between this value and this value can't be normally distributed because it's bounded at essentially at 1. None of these values can differ from each other by more than 1. And so the chi-square statistic is not actually correct. Now, if you've got lots of data in every cell, if your counts data is large in every cell, then it's a pretty darn good approximation. But it's often the case that you don't have a lot of members in any cell. Like maybe there's one judge who never holds hearings. And so if the value in any cell is small, and oftentimes people say 5 or fewer, using the chi-square test is not great. And if you see an expert doing that, you've got a basis for challenging them. There is this sort of cheesy fix known as the Yates correction, and I've shown that to you here. It's a different way of calculating that sum of squares, but really, this should not be here, really it's kind of a kludge that kind of sort of makes the chi-square test work, but I'm not a fan of kludges, and so what I now want to show you are two other tests that you can use that will determine whether your categorical data comes from two independent distributions, or whether you can basically disprove the notion that the two distributions are independent of each other. Do you remember when we talked about cross-entropy and the Kullback-Leibler divergence? These were techniques that we used and have used to measure the difference between two distributions. So we can try to use something like that here, because after all, we kind of generated two distributions. We have the original distribution of the observed distribution, and we have the null hypothesis distribution, which assumes statistical independence. So we could compute the Kullback-Leibler divergence between those two distributions, and maybe if that difference follows some other distribution, we could assess how likely it is that we would see the data we do if, in fact, the underlying distributions were independent. Now, it's a little more complicated than that. What we have to do is to compute the Kullback-Leibler divergence of the two distributions, multiply by 2, and then multiply by the number of people in the experiment. And for reasons I am not exactly clear on, to be honest, that will be chi-square distributed according with degrees of freedom as before, the rows minus 1 times the columns minus 1. So what I've done here is to write a function that does this computation using the log likelihood test, and we can run it on our counts data, and we get this array which is full of all sorts of obscure things. Let's take the numeric value of that, and what you'll see is, first of all, our statistic here is very similar to that produced from before, and our p-value is very similar. So I think this is actually a pretty good solution to the problems with the chi-square distribution. I don't actually think it's much harder to do the computation. Now, maybe in the old days when you couldn't do some of these computations, I could see it, but now it's not that hard, and so this is a respectable way of computing the likelihood that if the distributions, underlying distributions, were independent, you would see the degree of correlation that you do. There's another alternative to the chi-square test. And this one is rather beautiful, although it's a little bit complicated. But let's see if we can follow it. It's called the Fisher exact test. So the reason it was out of favor is it takes a lot of computation, but it's theoretically better. And since the computation isn't so hard, once you have fancy computers and things like Wolfram language, I rather like the Fisher exact test. Now, to understand the Fisher exact test, you need to understand a distribution that I don't think we've seen before, the multinomial distribution. It's sort of a generalization of a binomial distribution. If you remember the binomial distribution, you have a number of trials, n, and some probability that in any given trial, the output will be a 1, and of course an implicit probability, 1 minus p, that the output will be a 0. Okay, so we've got a parameter p, as well as a parameter n, the number of trials, but a parameter p that tells us the probability that any given output will be a 1, and obviously that means that the probability it will be a 0 is 1 minus p. So we could, for example, write the PDF of a binomial distribution with 7 draws, letting the probability that any particular draw will be a 1 be the symbolic parameter p, and we could evaluate that and say, hey, let's evaluate that at 3. All right, so we get an expression. Now what I want to do is, instead of writing it this way, I want to write the binomial distribution as a number of trials and a single probability p. I want to write it as that same number of trials, but to actually specify, okay, the probability of a 0 is 1 minus p, and the probability of a 1 is p. And if I do that, okay, so now I've fed that into the kernel. Now what I want to do is to compute the PDF that there are 4 zeros and 3 ones. And this is exactly the same thing I did here, right? What does 3 mean? It means that I want to see 3 ones. And if you see 3 ones and you have 7 draws, then you're going to see 4 zeros. So let's see what that is. And it's exactly the same thing as we saw above. So you can think of the binomial distribution as sort of being a simplified presentation of a multinomial distribution in cases where there are only 2 potential outputs, 0 and 1. But now we can generalize. Look, here we have 2 possible outputs, but we could have m. That is, you could have n trials and m different outputs. And each output has a probability such that the probabilities sum to 1, and the sum of the output values must sum to n. So we could generate 4 outcomes, and the probability of outcome 1 could be 2/10, and outcome 2 could be 4/10, and outcome 3 could be 1/10, and outcome 4 would be 3/10. And if I want 10 draws, here's what I write. Okay, here's the probability of each output, 0, 1, 2, 3. Here, or I'm sorry, 1, 2, 3, 4, it doesn't really matter how you number it. Here are the number of trials. We'll call this multi-4. And now I'll say, what is the probability of getting a 3, a 6, a 1, and a 0? That is 3 of the first kind, 6 of the second kind, 1 of the third kind, and 0 of the fourth kind. So we can compute that. And we can also ask, how likely is it that an outcome will be rarer than outcome 3610? And we have this function, rarer probability. That's really a lovely Wolfram language function that's going to compute that. And there it is. And let's actually compute the numeric value of that. And there we go. So there's a 9.6% likelihood that an output from this multinomial distribution would be rarer or rarer than the output 3610. With the multinomial distribution under our belt, it's now time to look at that Fisher exact test. Here's the idea. Our observed distribution has marginal totals. It has row totals, it has column totals. But there are ways I could rearrange the numbers in the cells that would preserve the observed marginals. And so what we want to do is to examine those possibilities. Let's just look at this for a moment here symbolically. Supposing this is my observed counts. Okay? And now what I want to do is find the set of values A, B, C, D, E, F, G, H, I, whose marginals, second marginal, is the same as the second marginal of our counts matrix. So here are our constraints. Here's what needs to be true. And we could do the same thing for the columns. We could say, I want the marginal totals of our columns to be the same as the marginal totals of our symbolic matrix A, B, C, D, E, F, G, H, I. All right. And we need to add one more constraint, which is that these numbers can't be negative, right? We can't have count data that's negative. So I'll call that cell constraints. There it is. And now I'm going to put the row constraints, column constraints, and cell constraints all together, join them, and call the result all constraints. All right, so those are our constraints. This is a matrix will preserve the marginals and have non-negative cell values if these things are true. And so now let's actually try to find all possible solutions that satisfy these constraints. All values A, B, C, D, E, F, G, H, I that satisfy the constraint. I will require that the solution be an integer and will call the result solve. Okay? Or, I'm sorry, this is actually a function, isn't it? It's going to say this is a function of the constraints. All right, and now what I'm going to do is I'm going to take all the constraints and run the solve function on it, and we will see how many possibilities there are. And it's thinking, takes a little while. All right, so here's a solution. A could be 0, and B could be 7, and C could be 18, and D could be 2, and E could be 41, and F could be 0, and G could be 32, and H could be 0, and I could be 0. Or let's just go down 85,000 solutions later. A could be 25, and B could be 0, and C could be 0, and D could be 9, etc. And by the way, you can see why before computers, Fisher exact test was not in vogue. All right, so we have whatever it is. How many solutions do we have? We have 85,575 solutions. Here's what I'm going to do. I'm going to represent the null hypothesis as a multinomial distribution. That is, the null hypothesis is essentially a matrix of values, right? We can see what, in fact, the expected probability array is. And if we multiply that by 100, which is how many people we have, this is the expected number of people in each of the cells, right? But if we just flatten this, let's go back to our original thing. If we just flatten this, we get the probability of a person falling into each of these cells. Judge 1, denied. Judge 2, granted. Judge 3, hearing. And so that's really just an input to a multinomial distribution with 100 trials. 100 because we have 100 people in all of the cells. So we're going to represent the null hypothesis now as a multinomial distribution. There we go. Now, let's calculate the likelihood of each consistent outcome. Let's calculate the PDF under this null multinomial distribution of each consistent outcome. So we are going to have to evaluate the PDF at 85,575 values, but that's what Wolfram language lives for. And it takes a moment, but there we go. We have 85,575 tiny numbers. Now, this is not a probability distribution. Why? Because these numbers don't sum to 1. What do they sum to? They sum to a little number. But if we divide each of these numbers by this total, then we will get numbers that sum to 1 and that can represent a probability distribution. So let's do it. All right. And we can just confirm that those do now sum to 1, lest there be any doubt. So now what we want to do is compute something akin to a rarer probability. What we want to do is find our distribution, find essentially its consistent outcome probability, and see what fraction of the consistent outcome probabilities are less than or equal to that value. And that will tell us whether we have an outcome that's fairly common under the null hypothesis, the multinomial representation of the null hypothesis, or whether we have something that's rather rare. To do this, I'm going to use select. I'm not sure if we've seen select, but here's how it works. Select 3, 4, 5, 6, 7, 8, 9, 10, 11, and we'll have some test. We'll say, is it a prime number? And it's going to pick out the numbers that are prime, and of course I could then say, you know what, add those up. Get me the sum of the prime numbers in this list. And so this is essentially what we're doing here. We're saying find me among all the consistent outcome probabilities, find me those these are probability values, find me those where the probability, and you see what I've done here is to compute it at my counts value and then divide it by that total number. Find me those that are rarer than what I have and add them up. And that is basically going to give us a rarer probability. And ka-chunk, ka-chunk, ka-chunk. 0.0124137. That is essentially the equivalent of a p-value. It's not quite a p-value, it's a rarer probability. But what it tells us is that there are very few outcomes that are rarer than this, and this is telling us that our outcome is pretty unlikely if the null hypothesis were true. So the Fisher exact test is basically the right way to deal with categorical data, but it does require a fair amount of computational horsepower. In conclusion, in this video I've shown you 3 tests for examining a null hypothesis that one distribution, like in this example the distribution of dispositions, is independent from another distribution, the distribution of judges. The simplest of these 3 tests is the ChiSquare process, and it could be done with pencil and paper, back in 1930, and it can certainly be done on a simple spreadsheet, and as a result, it's quite popular. But it's only an approximation, and it's not a particularly good approximation when some of the cells have low counts. So I've shown you 2 other tests that are better. I've shown you the log-likelihood test, which measures the Kullback-Leibler divergence between the null hypothesis of independence and the distribution you see. And I also showed the Fisher exact test, in which you transform the distribution of observations that you expect into a multinomial distribution, and you ask how unusual your outcome would be if that multinomial distribution, the null multinomial distribution, were in fact the case. So, thanks for watching, and I hope you learned a lot.